I'm Stefan, and I did this work together with my supervisor, Michael. And despite the title being in Greek, the talk will not be. First of all, a little bit about myself. I'm a PhD student at Saarland University. You might not have heard about this before. This is located in Germany, and I have a special slide for the Americans here. Germany is a country in the middle of Europe. You might recognize it because of people looking like him. And it was in early 2011 that, by the way, some of you might be too young to remember, 2011 was the time when SD cards only had a size of 32 gigabytes. And it was in early 2011 when the German government announced so-called IT security competence centers. And Saarland University became one of them. And we had to come up with a name for it. And, well, being straightforward, being rule-based German, it was Center for IT Security, Privacy, and Accountability, or short, CISPA. And remind you, that was in early 2011, and only in November 2011, the American counterpart, CISPA, which stands for Cyber Intelligence Sharing and Protection Act, came to life, but we have nothing to do with that. The title of the paper, as you could read in the summary, is Making Fine-Grained Memory Randomization Practical is a good word, by allowing code sharing. That's quite a mouthful, so it seems that we tried to fit the whole abstract into the title. So now you have an idea. Any questions? No? Good. Coming back to the Greek word, oxymoron, I chose that word because it stands for the combination of seemingly contradicting terms, and I believe this is what we did in this work. It wouldn't be in this session if it wouldn't be about code reuse attacks or ROP attacks, for example. And prominent defenses against code reuse attacks are, for example, fine-grained randomization. It's sort of the silver bullet that has been incepted in the last years. Here are some examples of papers that propose fine-grained randomization. The only problem with it is that if you have something that is very, very fine-grained, randomized even across the process boundaries, then shared libraries, the concept that we have for the last 20 years, doesn't really work anymore, because if there's different things in different processes, there's nothing you can share, really. And this is why this is a contradiction. And Oxymoron tries to solve this contradiction by proposing a solution that makes fine-grained memory randomization available and still enables code sharing. You're all familiar with code reuse attacks, I know, but for the video, I think it was a good idea to step through and recall how that works. So you have a program that consists of several instructions, and you reuse them in a way that it was never intended to be. Like in this example, you get a completely different meaning out of the text that was sort of benign. And when ASLR was invented, the people thought it would be a good idea to change the addresses of a program so that it resides at a different position in memory, and then the adversary doesn't know where to target his attack because the adversary doesn't have any addresses to play around with. The problem only is that once an address has been leaked, for example, a leaked pointer somewhere, a malformed printf statement or something like this, then the adversary can easily calculate the distance from the original address to the memory segment in which the code resides, because it was moved on block, so there's not really much entropy in there. And that doesn't really work, I'm sorry. So fine-grained randomization, in contrast, was invented so that the program itself, the code, is split up on a very fine-grained basis. That could be functions, that could be basic blocks, or even down to the level of instructions. Yeah, thank you. So the adversary does no longer know where certain gadgets reside, and hence cannot use them anymore. This is a good idea. Also, it's necessary to have a better in order to have a better security for two different processes, either of the same program or of different programs, to feature a different randomization, because otherwise an attacker could simply infer information he gathered from one process to another process, and this would be insecure. So it's the best to have different randomizations in different processes. And, well, that seems like we've solved the problem, right? Not quite. If you look at this screenshot from a very popular operating system from Redmond, you'll notice that in the task manager you have a column labeled shared working set. And what that is that the processes that run in your operating system do not just consist of their own memory, but in order to save memory, they share it with other programs. And of course, this is the same for Linux and OS X. If we have a little closer look at how that works, then we have two different applications running here at the same time in two different processes. One is an application on the left-hand side that you can use to look at kitten pics, and the other one is a program to print your USENIX PDFs, for example. They differ in the main executable because they have a different purpose. However, they are using the same C library, for example, the same threading library, so they have a lot of code in common, and it makes sense to actually share that code so that the code only resides in memory once, but you can use it as many times as you want. And how this is done is like this. Usually every address space in each process is like a transparent window, and you can see from that window the C library and the threading library, and they are loaded into the address space, but they actually only exist once in memory. And now I think the problem is apparent. When we randomize each of the libraries independently from each other, then there's nothing to share because there's nothing in common. One is randomized in one way, and the other one is randomized in another way. So code sharing doesn't work with all the solutions that have been proposed over the last years. Sorry. And we made this experiment, and the graph is to be read like this. This is the savings because of sharing. This is a clean installation of an Ubuntu 14.4 system, and after you install it and take a memory snapshot, you have a saving to be read like this. If you have a library that is 1 megabyte in size, and you start 2 processes using this library, then you save 1 megabyte, namely in the second process. If you have 10 processes, you save 9 megabytes and so on. So for the libc library, which every single process in this Ubuntu uses, you save a stunning 206 megabytes in space. And the same is true for all the other libraries, and they add up to 1.4 gigabytes. In other words, if we disable sharing in the kernel, we would need 1.4 gigabytes more RAM just to boot to the idle desktop. We didn't do anything yet. And it gets worse if we, for example, start Firefox. Well, now we try to find a solution that combines fine-grained memory randomization with the possibility to still share the code. It is contradicting, this is why it is oxymoron. And one possible solution could be to split the code into pieces and then share these pieces individually. They could be as small so that you have enough entropy, and at the same time, each piece could be shared individually amongst each process. Problem is, though, that it's still one big program, so it needs to be interconnected. And that means that, for example, a function in 1 wants to call a function that resides in piece 3. And this is theoretically possible, but if we take a closer look at piece 1, that means that the call that is encoded in piece 1 to 3, for example, has a binary representation of the instruction somehow. So it must say call 3. And if we do that, then we have already used this address. If we, in another process, want to have another randomization, that's not possible because it's encoded in this instruction. So either we can, again, only have the same randomization in each process, which we don't want for security reasons, or we cannot share. So this is also not a good idea. So you could think, okay, maybe we can have something like a layer of indirection, and we only call every function by some sort of label, like we would do in a programming language. I write call foo. It's possible in theory. Problem is security issues. How do we address the table? Is there a way to somehow conceal the address that the table is stored at? Can we use a register for that? But maybe the attacker could use a register. So that's all kind of fishy, and that doesn't really work, it turns out. And Oxymoron, you would have expected, does all that together. And I'm going to explain you in a second how that works. So it can hide all the addresses from the attacker. It has a different randomization in each process, and all the individual pieces can still be shared among each of the processes. And we did that by implementing a different x86 calling convention. And we labeled this new code then position and layout agnostic code. We could have also called it position and layout independent code, but then it would be PALIS, and that's weird. And for PALIS to understand, you need to know how x86 is structured. So here's a graph of x86. And in the upper left corner, you will find a very infamous x86 instruction because that's very old. It's a 16-bit feature called segmentation. And the thing is that nobody uses segmentation anymore. It's sort of a relic back from the 80s, before we had a memory management unit and virtual address spaces and different processes and so on. And what this segmentation allows you to do is to add an offset that is not encoded in the program. So for example, if the program encodes a call to the address D722B, then you can silently set an offset in the so-called global descriptor table, that's Intel speech, and this would then silently add 1,000 hex to your address, and your call would actually end up being D8 instead of D7 because we just added 1,000. And this will come in handy in a second. Another thing about the x86 is that it allows for very complex instructions. One of them is indirect calls. Take a look at this example. This is not just the call 1, 2, 3, 4. This is called star 1, 2, 3, 4. And what this does is quite bizarre. It actually, the processor, really like a little program, goes to the address 1, 2, 3, 4, and then decodes the value that is stored at that address, may it be 32-bit or 64-bit, in this case 9876. And then it pretends like you would have called 9876, and it'll come in handy. Because for our translation or indirection table that we call the Randomization-Agnostic translation table, we combine those two things. So that means we have the GDT, which will add an offset, when the offset is actually the address of the table, 1230, and if we call star 4, it'll add 1230 plus 4, that's 1234, in hex of course, and it'll dereference the value that is stored at that address. And this is a perfect building block for having an independent, a memory-independent or address-independent, let's say, representation of code addresses. That works for calls, of course, but that also works for referencing memory using like move instructions. A little detail that I won't have time to go into is that the way I presented it is not really possible, so we need to use specific registers that Intel introduced for segmentation, FS in this case, but you'll find the details in the paper. And the advantages, I think, are clear, because of this, the call instruction has now been transformed to something that is just an index called star 4, basically means call the 4th index of the RATTLE, of the translation table. And so if I randomize the program in different processes in different ways, then I will still end up with the same representation every time, that is called star 4. And so we can share the code because it'll be the same in every process, despite of the or a different permutation in every process with the different pieces. So to give you a little example, one of those pieces must now look like this. We fill it up with the original instructions that could either be done by a compiler modification, or it could also be done by using binary rewriting. In our implementation, we use binary rewriting to have some sort of legacy compatibility. One memory page that we can share between processes is given by the x86 architecture and is 4 kilobytes. And we have to fill it up with NOPs, maybe just like as a little padding, to, in the end, add a jump that goes through our translation table. It will simply connect piece 1 and piece 2 like it was in the original, so that you have the original program flow, that's all. And then those pieces, probably more than 2, are stored in the executable file and in all its library files on the disk. And starting a process then becomes quite simple. The operating system loader, which by the way does not need to be modified, can simply load the different pieces. It's like having several code sections, like in the hundreds or thousands of code sections. And if you start the process again, then it'll end up with a different layout. It's like having small ASLR sections. And as you can see, we have different addresses, and the pieces, because they're identical, can profit from sharing. This is an example how it is translated. So I won't go through every line here, but in the first one you can see that the original move instruction, which has a hard-coded address, was translated to something that will index the RATTLE, that is the %fs, it's like use the segment register please, at index 8a and move that to EDX instead of the original address. So now it's address independent. You might think, okay, if every memory access, every code branch, every move instruction and so on has to go through a layer of indirection, that might be quite slow. But interestingly, it turned out that it isn't. On average, when we used the spec benchmark tool, we had an overhead of 2.7% for going through the RATTLE. That's not much. And the page jumps 0.5%. Page jumps, I mean, this is the interconnecting of the pages, because of the pieces, I'm sorry, because the pieces have to stay in the original order in order to remain their semantics. And also the file size overhead is not that bad, because we have added more instructions. That is, first of all, the artificially inserted jumps to connect the pieces. And second of all, some of the instructions got bigger, because x86 usually, back in the 80s, this is where it comes from, encodes jumps in an 8-bit immediate value, and because the FS offset that we introduced needs to have a large and long instruction, that also adds to the amount of bytes. And that means we have an increase of 12%, and also the file header itself is increased by roughly 2%. This is because we now have not one code section, but for example, 100. And that'll basically conclude the talk, and I'm happy to take your questions. Of course, the details are much more involved, but I didn't have time to present them here.
Hi, thanks for a really interesting talk. My name is Indranil Banerjee from Qualcomm. So RATTLE seems to be, abstract primitive, which you have chosen to implement with stuff we have available on Intel processors.
Exactly.
Have you taken a look at maybe ARM or,
I did, but the problem with ARM, or no, the good thing, if you will, is that it is, sorry, that's my microphone. So the good thing is that it is a reduced instruction set. But as we rely on the fact that x86 can do all this magic with dereferencing automatically and so on, it doesn't seem that easy. So, I mean, in theory, of course, it's possible, it's Turing complete. But you would need probably 6 or 7 instructions instead of just replacing one.
Okay, thanks. I just wanted to hear that you've looked at it and you agree that it's not impossible.
No, it's possible, but I guess the performance impact might be slightly higher.
Thanks.
Kevin Snow, University of North Carolina, Chapel Hill. Very nice talk.
Thanks.
Thinking about from the perspective of the attacker that's trying to use a memory disclosure to dynamically map out memory and build their payload at runtime. I see how Oxymoron prevents one from scraping pointers from code. Have you put in any thought into scraping those pointers from the heap in the stack, object vtables, return addresses on the stack, et cetera, et cetera?
No, it's correct, first of all, that you can't recursively go through the instructions, disassemble them like you did in your GDrop paper. But on the other hand, it's not that easy to remove the actual addresses from the stack, because if you write something like call fs:4, the processor will actually put the address on the stack, like 2b, 7, 8, whatever. So you can't really prevent that. I mean, of course, it's possible to not use the FS addressing from the processor, but to write your own instructions, but that'll be more difficult, I guess. But the table itself, by the way, is also protected, even though I didn't mention it, because segmentation also allows you to put it in a different segment, which is not accessible from the usual data segment.
Okay, thank you.
Ben Lifshitz, MSR. So could you comment on how Oxymoron affects the ability to debug these binaries, especially if they're widely deployed in the field?
So your question was if it's still possible to debug them?
Well, how does it affect the ability to debug them once they're deployed?
Well, for our solution, we implemented a translation for the debug symbols. So that means that every, like for example, dwarf debug symbol that is embedded in the executable file also gets translated once the program is started. So if you attach GDB, that'll still work.
What about broad telemetry that's collected from, I don't know, many machines?
I'm not quite sure what you mean, to be honest.
Well, maybe we can take it offline. Okay.
Oh yeah, sure.
Hi, I'm Chao Zhang from UC Berkeley. I have a question about the tables. Basically, your solution moves all the absolute addresses into the tables and replace the core jump instructions. My question is that in some cases, there are some code pointers are not hard-coded in the code or data, but they are computed from the code.
Exactly, yeah.
How do you deal with this case?
They still work, because if they are computed from the code, that's usually done, for example, in position-independent code by calling the next instruction and then popping the return address, like in RBX or something. And then you calculate with RBX. That's very common for switch statements, so that you have like an index, like switch I, and then case 0, 1, 2, 3 is like a multiple of that I. So that means that they use the current address that they got from the call instruction that pushed the return address on the stack. So if it's calculated on the fly, because it's position independent code, then it's easy because it knows where it runs. If it is a program that is not position independent, but it would really say add and then a valid address and I, or a multiple of I, then the rewriter takes care of it. Or if you use a compiler, the compiler would just replace it with an FS something instruction.
Okay, thank you.
Cynthia Irvin, Naval Postgraduate School. So getting to the compiler part of this, moving it practically forward, you've got a great demo here, but I only know of one compiler that works with segmentation. How would you move this forward to a practical application?
So I didn't implement the compiler part, as I said, the rewriting part.
I know,
yeah.
You did rewriting, but if people wanted to do this and use a compiler,
the parts of segmentation we use, they already implemented in LLVM and GCC. For example, GCC uses a similar segmentation trick to address thread local storage. So that's stored in GS. This is why we used FS, because it's sort of empty. And so I guess the support is there, but to be honest, I just had a brief look at the source code, so I can't really validate it.
okay.
David LeBlanc, Microsoft. You said this was x86 specific and that you looked at ARM. What about x64?
It's not implemented for x64, but as far as I know, it should work because the rudimentary implementation of segmentation still works. The only problem is that you can no longer set a limit to a segment. So the RATTLE cannot be hidden, because currently it's hidden because the code segment is just short enough of the RATTLE. So if you try to access the RATTLE using code, it'll not work. And my understanding is that the 64-bit x86 architecture does not allow you to set a limit, and that the FS, GS, and ES registers hold the offset directly instead of being a pointer into the GDT. So that means it's still secure, I guess, but not as secure as in the 32-bit world, because you could, in theory, have an instruction that says move FS to EAX, and then you have a general purpose register which holds the offset. But I think it's rare to find such an instruction because the compiler should take care that such an instruction does not exist. But that's a vague thing, I know.
Thank you.
So am I holding you back from lunch?
Any other questions? Okay, let's thank Stefan again.